Welcome to the inaugural Samtech Geek Speak webinar series. We're very excited to welcome everybody to this inaugural effort. My name is Matt Burns. I'm the Technical Marketing Manager here at Samtech. We're very excited to bring this new webinar series to you as we take advantage of the opportunity to interact with leading engineers across the industry. Before we jump into the presentation, just a little bit of housekeeping. We do have Q&A sessions available throughout the presentation. So if you have a question, please just enter that into the Q&A box and we'll try to answer that real time. Joining me also is one of my colleagues, Scott McMurrow. Scott's CTO of our Signal Integrity Group. Before we get started into the presentation, Scott has a few thoughts he'd like to share with everybody. Scott, take it away.
Thanks, Matt. I am Scott McMorrow, CTO of Samtech Signal Integrity Group, and I want to welcome you to our inaugural Geek Speak webinar series. Since we're all a lot of us are at home, we figured this would be a good way to present some meaningful technical information each week. Hopefully this will continue to run throughout the summer because looks like we've got some a substantial amount of attendance here. The purpose of this is to present meaningful technical information with no commercial plugs whatsoever. The idea is to develop a dialogue. We can't do it by voice since that would be total chaos with 150 people on this presentation. So we're going to do that through questions and answers. I am going to be the moderator of questions and answers throughout these different sessions that we have, and hopefully we'll be able to get to everybody's information that everybody would like to have. The layout of our presentation is that we expect it to take about 20 minutes to go through the basic slides. And then at that point, we would like to open up to questions and answers. And just to continue that dialogue organically, I'll field some of them in text. You'll all be able to see the answered questions. Steve Kruzwick will be able to answer with voice and may even pull up additional information if time permits. Additionally, if you didn't get your question answered during the presentation and it still is important to you, you can always contact us. The contact information will be on the last slide. And we'll be happy to schedule some private time with you and also in whatever needs that you have. Having said all that, Steve Kruzwick is here to present on PCI Express. Is 85 ohms really needed? Steve has 17 years of high-speed signal integrity experience with Intel and now Samtech. He's written a book on signal integrity. He has done lots of papers, presentations, and designs over the years. He has specialized in PCI Express almost since the beginning of the standard. And he is our expert at Samtech on PCI Express, connector design, interconnect design, and system applications. He'll be talking about this, and with no further ado, let me give you Steve Kruzwick. Thank you.
Okay, thank you, Scott, and thank you, Matt. I hope today I can take the 20 minutes and then the questions after to shed some light on the popular question, do we really need 85 ohms in PCI Express? So let's introduce why this is a question that we maybe have conflict with. imagine that you're a system designer, or maybe you already are, and you have so many I/O that you need to consider in your platform: USB, SATA, Ethernet, and you've got PCI Express too. And you only get one stack up for that design. You've got many impedances that you've got to meet. Do you have to get that PCI Express interface down to 85 ohms? If not the stack up, what about going through a connector, a daughter card that you may have 3 or 4 different I/O going through it? How do you choose the impedance for that connector if you're using USB, SATA, SAS, everything at the same time? So, to the bullets that you see on the slide, we want to try and follow that mantra for PCI Express. Is it appropriate? Do we have to do it for our packages, traces, cables, and vias? Because sometimes that's difficult. And we believe that we're following the specification and what it says. And we think it says we want to use 85 ohms, and that's optimal. And maybe we try to, but sometimes we can't get components. Maybe they're not available. So why is that? Maybe supplier devices aren't terminated to 85 ohms, are terminated to 100 instead. So what does that mean for my impedance? I want to try and answer some of those questions as we go forward. So first, the history. We should start and try to understand why PCI Express is 85 ohms. To go back to this time, we actually looked around year 2000 when PCI SIG wanted to enable as many PCB houses really around the world as possible. And one of the challenges they were facing was sometimes these narrow traces in your stack-ups that were used to reach 100 ohms would sometimes crack. And so the question was, could we widen those traces to reduce fallout? And if we were to do so, what's the effect for SI? Well, it actually turns out that a lower impedance at the time was actually better. We look at your kind of Gen 1, Gen 2 timeframe PCI Express interconnect, and you're experiencing very capacitive features, the transmit die, a package BGA or LGA, and especially connector plated through hole and press fit designs that are much less than 70 ohms with the large 28 mil drill and large pads. Then perhaps you've also got sockets that are greater than 100 ohms, so sort of some high impedance items, connectors that are greater than 100 ohms. At the end of the day, it was actually found a lower impedance from wider traces to reduce fallout was actually better for SI. And you can see that in the illustration. Here is a 100 ohm design channel in red compared next to an 85 ohm channel in green, where the TDR really shows fewer bumps in the road if the impedance is at 85. The large bump here being one of these Gen 2 era through-hole press fit style connectors that are very capacitively loaded. And here, to be honest, this is the best case. This is no via stub at all. And you see it's going down quite low with respect to 85. Together, those things are a net improved return loss. On the right-hand side of the screen, you can see that the return loss has gone down from the 100 ohm condition down to the 85 ohm condition. So at that time, hey, green light, 85 ohms, it's making sense, better than 100 ohms with the technology at the time. So let's understand something about what the specification says and what we can find in it. So there are two different kinds of designs in PCI Express, and we can put everything in two buckets. You either have a PCI Express design that is an openly interoperable CHEM topology, where I've got a plug-in card or a motherboard that I can use with any other plug-in card and motherboard that you get from Best Buy or Amazon or anywhere else. Then you have everything else. You might have mezzanine connectors, you might have backplane connectors, you might have cables, you may have no connectors at all, 2 chips on the same device. And you might have 3 connectors. Everything else has been considered a captive link. So let's outline what we find in the PCI Express specification. First, we'll check the box. 85 ohms is defined as required for PCB impedance for the interoperable bucket, adding cards and motherboards that play with each other. They're designed that way so that they match each other. Your motherboard is the same impedance as your adding card, and you get a net minimum return loss that way. Let's not marry an 85 ohm card with a 100 ohm motherboard. That's the idea. So everything else, 85 ohms does not necessarily apply. So outside of the chem spec, we would then refer to what the base spec might say about our other components, such as packages or cables or connectors. And what we find is packages are not necessarily required to be 85 ohms. If you find that your perhaps via through the core of your package may make sense with a trace impedance other than 85, it's completely acceptable. Okay, you're dealing with a lot of constraints in a package, BGA exit, and your C downloading. So it's unique for everyone. Those PCBs outside of the captive system, they don't have to be 85 ohms if you've got a non-interoperable environment. Connectors are also highlighted specifically as not requiring to be 85 ohms. And lastly, cables are not bound to 85 ohms. And in the middle of the page, you can see the excerpt I've taken from the PCI Express spec. This is out of the chem spec here, where you do see the definition for the PCB trace impedance to be 85 ohms at the top. And this is defined indirectly as a limit from 68 to 105. So you can then intuitively decide, okay, 85 ohms plus or minus maybe 12% is what's defined here. Everything else I've highlighted, the requirement doesn't apply to vias, connectors, packages, traces. Do the diligence to minimize the reflection and pick the impedance that's right for you for those devices is actually what is said there. So you have the freedom to decide what's best for you. So let's consider some of these cases. First, PCB impedance. There are maybe some motivations to use 85 ohms in your design. There are some upsides to it. Typically, wider traces, lower loss compared to 100 ohms. That could certainly be a benefit. Quite frequently, 85 ohms is a good match to a dense BGA pin field where the density keeps you from opening up the antipads significantly. And then your characteristic impedance in the BGA region is low. So you may actually benefit from an 85 ohm trace. 85 ohms is easier to achieve on a stack up with really thin dielectrics and high layer counts. Package impedance for most PCI Express devices is already going to be 85 ohms most of the time. Okay, so matching it may make sense. Device termination, we sometimes talk about, we see it's 100 ohms, but PCI Express is routed at 85. I would submit that actually 85 is still approximately not optimal, even though the device termination is 100 ohms. It is a AC effect that you're looking at with the reflection, and the capacitive load at the termination effectively creates a lower impedance that you're seeing. So I wouldn't think about termination as being truly 100 ohms. So I put this as an argument for maybe 100 ohms. Maybe 85 ohms makes sense for that reason. 85 ohms is typically less crosstalk. If stack up's constant. And your wider traces would be more tolerant to impedance variation.
Say, Steve, we have a quick question from Kanan Munsell. And his question is, how is 85 ohms less loss than 100 ohm in the same stack up? Isn't the capacitance larger? Wider trace equal more capacitance between the reference and conductor? If you could just a quick answer to that, I think that would be helpful for a lot of people.
Yeah, I think the quick answer is that while the capacitance might be less, I think that you see a decrease in your DC loss and your area, giving you a lower loss throughout the frequency spectrum. That's what I believe. Is there any other opinion on that?
Oh, thank you.
Okay, good.
Question. How is crosstalk reduced by using 85 ohms?
The capacitance increase with 85 ohms sort of goes hand in hand with the crosstalk question. So as you widen the trace width and keep dielectric constant, you're more close. You're more heavily coupled to the ground plane, and you'll have fewer fringe fields going out to the next pair if distance did not change.
All right. Thank you, Steve.
Yeah, very good questions. Good. I see the Q&A panel now. A couple motivators, and maybe there's more that aren't mentioned here, but reasons for higher impedance are going to be that perhaps in your design, 92 or 100 ohms is a better match for the connectors or cables that are being used in your system. We'll probably unpack that more in another slide. Another reason is that the devices that you're supporting may not be 100 ohms, may not be 85 ohms in the trace impedance for your packages. And this is actually quite common when you see a device that maybe supports Ethernet and supports SAS or SATA and supports PCI Express at the same time. That device vendor has to choose maybe one impedance for all of those I/O on the same lane. So you can see some devices maybe not being 85 ohms, and maybe you can make a choice that better matches that device. So there are some reasons out there to not use 85 on the PCB.
Hey, Steve. We got a question that came in via the chat, and Ted Purcell asked, why is 85 ohms more tolerant to impedance variation?
So the reason is if you assume that your etch variation for your traces is constant, whether you're 85 or 100, or whether you're a 4 mil trace or a 5 mil trace, you're going to experience potentially a half a mil variation. And when you have the wider trace, then a smaller percentage of your overall trace width would be affected by that tolerance change. And if a smaller percentage is being changed by that constant half a mil value, then you see less drop in impedance due to variation in etch.
Thank you.
Very good. Last item on this slide is, how do I decide? There's all these questions, all these points. I think first we might review the S parameter. How does the overall performance look? For PCI Express, the normative method to make the final decision on your impedance is through full channel simulation. And so this would be with like a tool available from PCI SIG, CSIM, or similar that offer you the capability to put in the channel S parameter and then test it against the compliance I height and I width. And then through that means you could compare 85 ohms versus 100 ohms or some other impedance. Okay, let's think about connectors. So the title of the slide, Components Today Outside of 85 ohms, is okay. So I want to talk to that. Connectors today are seeing variable dielectric experiences as the signal passes through them. So unlike in a PCB, you've got a mixture of air and plastic. And it's very common with that lower effective dielectric constant to see impedances above 85 ohms in connectors. I'd even go as far as to say your Gen 3, Gen 4 era surface mount connectors that don't have a large press fit via pulling them down in impedance are experiencing higher impedances, maybe as high as 120 ohms is what I would submit to you. So they can be quite high at the time. The thing about that is connectors are really not uniform transmission lines. There's air, there's plastic, there's retention features, there's surface mount pads, there's gold finger pads that your connectors latch onto. There's lots of variation, and that's quite common. I want to give you an example. The TDR in the bottom left offers two Gen 5 32 gigabit capable connector responses. And again, what you see here is that connector impedance it's not really uniform. It's affected by all those variations that are possible. So what would you say? What impedance are either of these two connectors? One person might describe it as an average value. Another individual might describe the connector impedance by the maximum value. I think you would actually get different answers. And I would actually submit to you that if you could make one of these connectors, ideally 85 ohms in the body, that may not actually be optimal. Consider most connectors in any form factor have a large solder pad or BGA pad or gold finger on each end that's very capacitive. And I would suggest that perhaps a higher impedance for the connector body can actually be beneficial to pre-compensate those low impedances that are coming before or after it. So maybe 85 ohms isn't even the right answer for that point of view. So let's look to the right. We have two connectors with different impedances. On the right, we have the return loss. And even though one of these Gen 5 options is momentarily over 100 ohms, both are considered compliant to or spec or target for 32 gig. And the reason for this is that even though the connector may go above 100 ohms, that occurrence of high impedance is very brief, and it's not significant enough to raise the return loss at 16 gigahertz and below. And you might note that the return loss goes above 10 dB at the higher band. But for the application here, you can actually demonstrate you're still below 10 dB.
So Steve, we have several questions. The first one that would be good to talk about here. The first one is S parameter simulation or measurement. Should the port impedance be changed to match 42.5 ohms? And I think that's a good question with respect to the drivers and receivers in PCI Express.
That's a good question. I think it goes to where you're applying the S parameter, what it represents. If your S parameter represents a connector that's going to see 85 ohms PCB on either side of it, then I think 42.5 ohms, yes, it makes sense. If your S parameter represents the entire length from C die to C die, then maybe 50 ohms would make the most sense.
And I just want to follow up on that, and that's that even though PCI Express specifies 85 ohms for the printed circuit boards in a CEM-based system, the actual silicon is not 85 ohms. Generally, the output impedance is actually higher because of power considerations. One more question. Is it safe to look at component compliance only to the Nyquist frequency?
It's a power spectral question, right? So at Nyquist, like 40%, I think, or so of your energy is passed through at that frequency. So I would suggest that there is a dependency above Nyquist. So is it safe to stop at Nyquist? You can build confidence if you go a little bit beyond it, I believe. I think you'll see that in the latest PCI Express specs. I think as they become published, I think they're targeting they're targeting 50% beyond Nyquist.
And I'll just follow up with that. That typically matches the receiver filtering that's used, which is usually about the 3 dB or 6 dB point is usually about 50% higher than the Nyquist frequency in order to achieve good recovery.
Mm-hmm.
Hey,
So,
Steve.
yeah.
Hey, sorry if I interrupted your train of thought. We have a question that was submitted via the chat about the reports here. Are the impedance reports based on measurements or simulation?
Well, the curves here are simulations that I'm using here. We would have measurements for our products, but for the purpose, it's a simulation here.
Thank you.
Yeah, good question. I had like one or two more comments I wanted to make on this slide. I think the question is, one of the questions is, you see that the return loss increases when you go above 100 ohms and you're still Gen 5 compliant. I think what PCI SIG is intending to communicate here is think about return loss as how much deviation away from 85 ohms is permissible for a Gen 5 connector at this data rate or a Gen 4 connector at this data rate. And that's why we have the 10 dB return loss limit. That's why we have connectors that are a little bit higher. How much deviation away from that 85 ohms reference is reasonable? If PCI SIG believed that connectors perfectly close to 85 ohms was required to make systems work, we would see that in the return loss limit. The return loss limit would be very tight, minus 40, minus 50, 60 dB of return loss, exaggerating a little bit, but you would see a very stringent tightening if exactly 85 ohms is what was needed to have a successful PCI Express system. I want to look at cable now.
Just a couple of more questions. Sorry about that. If we move to 100 ohm systems for Gen 5, are we not moving away from all the benefits at 85 ohms? It's a good question.
Mm-hmm. I guess that must be in reference to the peak connector impedance, the green curve on this page. And what I would suggest to you is you get a different answer. Like you're describing this connector as 105 ohms, but you may ask someone else and they would say, well, maybe the connector is 90 ohms on average. Here, the question, you could do the analysis if my channel is at 85 ohms or 92 ohms and perhaps compare to see what were better. I would suggest to you if you brought it up to 101 ohms for the trace impedance, that may not be beneficial because of the large pads on each side of the connector. So I don't know. I wouldn't look at this plot and advocate for a 100 ohm trace immediately, if that makes any sense.
And then one more question. I think this is also a good one. How do we use TDR for PCI Express Gen 6 running PAM4?
Yeah, that's a good question. I think with PAM4, you're going to have the increased sensitivity to return loss with the reduced SNR that comes with PAM4. I think we still have the TDR for information gathering, but I think we start to interpret it differently, and we start to maybe interpret our reflections as they matter more than we would have thought previously.
Thanks, Steve.
Okay, good. Okay, so cable consideration. Maybe designing a system where you use cable to get from board to board, or reduce your PCB losses by using low loss cable. Typically, we think that we want to choose cable impedance to match the PCB impedance. Makes intuitive sense. We actually hear it quite a bit. Hey, I want to get 85 ohms cable into my design. That might be great and fine, and it might help your low frequency return loss. But what I want to ask is, what about the interaction between the cable impedance and the board impedance and the mating connector that goes in between the two? I'll show you an example on the bottom left is a TDR of a PCI Express 85 ohm channel, and then introducing three different cable impedances, 85, 92, and 100. And what I see here is potentially a trade-off in the decision making. The 85 ohm solution might offer the lowest frequency return loss improvement because it's going to match the PCB impedance on either side and keep you as flat as possible. But the 92.5 ohms is an interesting curve because it seems to better match the mating connector. And I want to call that out with a highlight on the slide. In the TDR, you can see where you go from the 85 ohm trace up to a 93 ohm mating connector, and then potentially into a 93 ohm cable. And I think this is a really important point to make that you can see in the TDR, that your reflections, if you solely want to manage reflections and reduce them, then your cable impedance selection needs to think about and comprehend what's going on with that mating connector that the cable is attached to. What is its impedance, and how much reflection am I going to see based on the cable impedance that I choose? And then I think it really has less to do with the PCB that has come before it. By the way, the PCB has already experienced its primary reflection against the mating connector, not necessarily against the impedance. So I think that's a sobering thing to think about as we go into higher speeds. It's not just about what the PCB was, but also how does your connector perform. And I have another learning, probably to make things more complicated and more complex. In our learning here at Samtec, we've observed that lower losses can be obtained in cable with higher impedance. It's a little counterintuitive because this is the opposite trend that you would experience in PCB that we just talked about, where lower impedance in the PCB is improved loss. We actually see the reverse, and then this is due to the geometry inside of the cable. But then this makes selecting the optimal impedance for cable sometimes a little bit difficult. Does your application need more benefit from a loss improvement or more benefit from reflection improvement? And so, looking at maybe the SNR of your entire system through a channel simulation is a prudent way to answer some of those complex questions. Let's look at the return loss. For the same topology I just reviewed for you on the previous page, so 85, 92, 100 ohm cable. And we could see it in the TDR and make a judgment, but when we look at the return loss, this is a common problem, right? The return loss curves, they look so similar. And it's difficult to assess which was maybe the optimal impedance in the return loss, 192.85. The differences, they look negligible. They probably are negligible. It's hard to sort this out. The best solution, the normative solution I mentioned once, the channel simulation approach with CSIM, will give you the answer, the net effect of all the pros and cons. But it's costly. You have to set up the simulation. You have to have all of your S parameters. I want to submit to you that in lieu of channel simulation, we can discover a first order answer in the impedance and return loss question through single value metrics. And there are a lot of choices that are out in other standards and other tools that you can look at. They're going to include effective return loss, ERL, RILN, reflection insertion loss noise, IMR from USB, integration of the return loss, etc. There are a lot of things that you could look at to potentially give you a single number rating to a curve like this that is hard to pick out the best one, right? So I'll give you the answer for this return loss. We take the whole channel that we observed on the last page and this return loss curve and provide a full channel ERL, effective return loss calculation, which is coming from the IEEE standards for channel and package compliance. And we test it on the PCI Express channel, 195.85. Who wins? The 92 ohm. The 92 ohm cable has the higher SNR as it comes to reflection. So example, and really the last example that I have for you today, is this here, a recently developed platform that we did that has a purpose to demonstrate artificial intelligence or machine learning-like topologies. This might be sort of familiar to you with the edge cards and the cables going between them. We intended to use this to demo for live silicon, where we would put one silicon on one end and transmit to the other. The topology includes, highlighted on the picture, a short PCB trace, about 2 inches of 85 ohm route, a right angle connector, 12 inches of cable, and then repeat on the other side. So for the development of this platform, we asked ourselves, what should we do with the cable? Should we route the cable at 85 ohms, or should we choose the 100 ohm cable? And to make this decision, we used the full link BER CSIM simulation like I advocated for. And the finding here was that you can see the arrow, higher eye height and higher eye width for the 100 ohm cable compared to the 85 ohm cable. And the explanation here is that this topology seemed to be benefiting from the loss improvement available on the 100 ohm cable. And that, so I know what you're going to ask. You're going to ask, well, Steve, how about the 92 ohm cable? You're not showing it here, but it might have a better return loss, even though the loss might not be as great. So if you're asking this question, then I have to say, I think I've reached my goal in this presentation, because you're looking at the topology and you're thinking about what impedance is best here, and you're thinking about something other than 85, and not thinking that 85 ohms is your must-have impedance. So I think that's great. So in closing, I hope that you've learned a little bit about what the specification says is and is not required for 85 ohms. To recap, really the only item that's ever required to be 85 ohms is the PCB route in chem interoperable topologies. I think the second bullet here, I think that as we see devices try to straddle multiple interfaces and components try to support multiple interfaces, I think you're going to see an increase in applications, devices, and components out on the market that are maybe 92 ohms instead of 85, in order to balance all the things that are at play. And I hope that you take away that connectors and cable impedances other than 85 ohms could potentially add value to your specific applications. So thank you for the time. I really appreciate it. And we'll see what other questions we have.
Oh, we have a few questions, Steve. Let's back up just a couple of slides. There we go. So we have one question from Boris, who's, what's the connector characteristic impedance for this particular example?
For this particular example here, let me flip back maybe one more page because you can see it in the TDR. Characteristic impedance is usually defined as the 2D instantaneous impedance, right? And so I'd have to look at the arrow that's pointing here to this connector. And if I had to give you one number, I'd give you 93. Although like any connector, it deviates a little bit through the length of its body. You can see it goes up and goes down a little bit.
And one more question, and I think this goes to your presentation. What would a simulation where the PCB is also 100 ohms along with the cable, what do you think that would look like?
Hey, that's an interesting solution too, right? You'd have, let's give it a number, you'd still have a 7 ohm reflection from the PCB down to the 93 ohm connector and then back up to 100 ohm cable. It's an interesting scenario. I think there's a myriad of things to try, and to be honest, I don't know what the final answer would be. Some diligence could be done to try it, right? What do you do when you still have the package and you have the BGA escape in the package and its impedance is lingering below 70 ohms? So that's a little scary to me to possibly connect a 100 ohm trace to that.
I agree, Steve. This sort of points out if you look at the way this TDR looks, we're basically gently stepping through the different impedances that are presented to us by elements in the system. And the best response always tends to be to just go with the way the waves are going. So go to 85 ohms coming out of the package into the connector, which tends to have high impedance section, run it a little bit higher, and then come back down on the other end. So that's always a good plan. What is the impedance tolerance for bulk cable? Maybe I can answer that.
Yeah, can you take it? Yeah,
our specification. Our specification worst case for our twin-ax cable is plus and minus 5% from nominal. Typically, it's much lower than that. I can't speak for other cable in the industry, however. Do future PCI standards have plans to move from the frequency domain masks to something similar to IEEE COM and ERL?
It's been discussed. I don't know if that would be something that would be realized or not. I do have a future webinar in this series to talk about single metrics for PCI Express crosstalk, where we will use ICN.
Is there a motivation or reason to make connectors that are 85 ohms?
Yeah, I mean, some do exist. It's possible to do that. No 85 ohm connector is really going to be like completely flat along the 85 ohm line. It's going to have ripple up and ripple down, right? And so if you can, and it's going to depend on the application and the bandwidth. So you would ask yourself, for the speed I'm running, how close to 85 ohms do I really need to be? The answer for Gen 5 is that you get great performance even when you're in the 90s for impedance.
Thanks. Is there any motivation or reason? I'm sorry, that one's, we've already done that one. Does differential impedance in the board also need to be maintained at 85 ohm or for better return loss?
Differential via design?
Yes.
Yeah, I would recommend it. Yeah. Size your anti-pads and your drill size if possible. I think at Gen 5, in Gen 5 applications, it's very important. Back drill if you can, etc.
Connectors are typically stated with 50 and 100 ohm impedances. Do our connectors have an optimized impedance value? How do we determine this?
Typically, at Samtec, we will offer reference impedance that the connector is intended to be used with. That's usually either 100 ohms or 92.5 or 85 ohms. I think you should be able to get that from our SI collateral when it's provided. And the TDR would reveal how close one is to that mark. There's always some variation.
Okay, here's a specification kind of question. Nick asks, thanks, Steve. Steve made a reference that some of the performance metrics in Gen 5 are defined till Nyquist plus 50% of Nyquist. Would you happen to remember what parameters this is defined for in the version of the spec?
So I guess I can't comment on unreleased PCI Express documents, right? So this is probably something to watch out for.
Okay, thanks. And what is the rise time of the TDR measurement, and how does it compare to the actual silicon in this case?
Oh, good question. In our simulation, we used 12 picoseconds in the TDR that's shown here. Let's see, perhaps at a Gen 4 transmitter, you might see close to 12 or a little bit faster. And if that were the case, you'd see a little bit more impedance variation in the TDR.
What rise times are we seeing for Gen 5 and expect for 5 and 6?
So the Gen 5 UI, I think isn't it 18 picoseconds? So you might say a 20 to 80% rise time is going to be close to 10 to 12, maybe 8 to 12. Depends on how you define it.
All right, everybody. We're 4 minutes after the hour. The queue of questions has ended, except there's one. What is the name of the connector system you're presenting now by the anonymous attendee?
The anonymous attendee, okay. The one that you're looking at on the screen now is the Accelerate cable system.
Okay, thank you.
Hey, Scott.
Yes.
Sorry to interrupt. We do have one other question on the chat. On the TDR plot on the left-hand side, why is the package impedance so low, around 65 ohms?
That is the capacitive load of the transmitting CDI.
Thank you.
So it's a 50 ohm resistor in parallel with what might be like half a buff.
Yeah, about 125 femto. Well, no, more like about 400
No.
femtofarads.
Yeah, so maybe 400. So that value is built into the Gen 5 reference package. You can't like see it directly, but it's on that order of 0.4.
What is the termination impedance that you use to see this TDR?
85 ohms, 42.5.
So Boris asked, in PCI base 5 spec, it specified RX tolerancing interconnect environment are 85 ohm differential for 16 and 32 gigabit per second channels. Not sure what that is getting to.
I think he's making the comment that when receiver devices are tested, PCI SIG built a reference platform, and they had to choose an impedance for that, and they did in fact choose 85 ohms. What that means is that all PCI Express devices out in the world were validated against the 85 ohm PCB coming into the package. That's what they were tested against and proved compliant. So it sort of just really reaffirms the point. If you want to pick an impedance for your application, you just need to do the diligence and validate that the impedance you're picking is going to make sense.
And then finally, I'm not sure we can answer this. What are the equivalent RLC delay parameters for a PCI Express Gen 3 connector that could be used in simulation if you don't have the S parameters?
Right, that's a tough question. I don't know that we can answer it right now. We could take it offline maybe.
All right, if you could go to the last page of the slides.
Last page, okay. Oops, too far. Here? No.
No, the last page.
One more.
The final,
Okay.
The final slide.
The final. Okay.
Yeah, sorry, the final.
Final. Okay, this one.
So yeah, we're getting close to 15 past the hour. So we've been in this for almost an hour now. What I would like to do is thank you all for being here, listening to Steve. We plan on presenting these once a week for, well, as long as we can come up with good ideas. If there are questions that you have not had answered that you would like to have answered, you can go to, about this presentation, go to geekspeak@samtech.com. You're on our mailing list from having subscribed to this presentation. And so as a result, you will get a link to the video presentation, also to the presentation slides. And of course, at any time you have any questions about signal integrity, you can contact us at sig@samtech.com. This time is reserved 2:15 Eastern time and 11:15 West Coast time is reserved for our Geek Speak presentations. Our next presentation will be will be about TwinAx, and it'll be basically a guide to TwinAx. We have further presentations that are going to be scheduled. TwinAx Basics is next week. After that, we have DC power distribution. And after that, I believe we are going to be, presenting glass weave, fiberglass weave. And we're scheduled right now all the way out through the end of August. So please come and join us in your stay at home and work at home. And let's do this together. Lots of good topics, lots of good things. If you have any more questions, please respond to just send us an email. And if you have any suggestions for other topics, feel free to send those. We'll be sending out our links for the next presentations immediately. So if you want to get on the attendee list for next week, do it as soon as you possibly can. Matt, do you have anything else to say?
I just want to thank everybody for dialing in. Great job by Steve and Scott. And we look forward to connecting with our engineering colleagues over the coming weeks and months through GeekSpeak.
Okay. Thank you, everyone, and stay safe.